This lesson introduces the law of sines, and like the law of cosines, this is another way that we can find missing sides or missing angles to solve in a general triangle. So it doesn't need to be a right triangle anymore. We can solve any triangle. And the law of sines says that the sine of an angle, the ratio of the sine of an angle over the side opposite that angle is the same as in the same triangle, the sine of another angle over the side opposite that is the same as the ratio of the sine of the third angle over this third side. So anyway, this holds. I can set, equate those two, any two sides. I can equate these two. I can equate those two. And of course I could flip the entire thing over and put the sides on top and the sines of the angles in the denominator, and the law holds. So it deserves a simple proof so that we know kind of where this comes from, to see it for ourselves using right triangles. So I have here a scalene triangle ABC, and I'm going to label the side lengths. This is side A over here and side C, and I don't need, this side B is down here. I don't need it for purposes of this proof, but what I want to do is drop an altitude from angle B down to side B and create two back-to-back right triangles. And then I'm going to look at each of the right triangles and talk about the law of sines, or talk about sines. So in this right triangle here, with respect to angle A, I can say that the sine of angle A is the ratio of, let's call this H for now, that height line, since it's just temporary. So the sine of angle A is opposite over hypotenuse in this right triangle, so it's the ratio of H over C. And then in the right triangle on the right, with respect to angle C, I can say that the sine of angle C, the ratio of opposite over hypotenuse, is H over A. Then, because I do want to eliminate the H, I can use H to link these two. I can solve each of these for H. So with this equation, if I multiply both sides by C, I will have isolated, and I'll have H equals C times the sine of angle A. And in this equation, if I multiply both sides by A, I'll isolate the H, and I'll have H is equal to A times the sine of C. And since H is the same in the big triangle, it's just this length, whatever it is, these two expressions represent the same value. So I can equate them. So C times the sine of angle A is equal to A times the sine of angle C. And then, finally, to achieve that equality right there, that the sine of angle A over A is equal to the sine of C over C, I can simply divide. I've got to divide out the C on this side, and on this side the A. So I have to divide both sides by C and both sides by A. So I get a cancellation here and here, and so I end with the sine of angle A, the ratio of that sine of angle A over side A is equal to the same ratio, sine of angle C over the length of side C. Oops. Okay, which is these two right here. And of course, I could continue. I could do this over and over again. I could do it. I could drop an altitude from angle A or from angle C and prove that all three of those ratios are equivalent. So that's the little proof, and now we'll look at a simple example of using the law of sines. So in this example, I have triangle ABC, and angle B is 52 degrees. So I'm just going to pick one of these angles. I'll make this A, I'll make this B, make this C. That looks like that could be a 52-degree angle or so. It's an acute angle. And side A, which is opposite angle A, is 3. And side B, which is opposite angle B, is 4. And I have to find angle A. This is what I have to find to the nearest tenth of a degree. So notice that I do have an angle and its opposite side that I know, and I can use that law of sines to equate this other side length I know and that angle. So I'm going to use the sine of B is to side B as this would be side A, as the sine of whatever angle A is to side, to 3. Well, no, well, to side A. And then we'll plug in the numbers now. Okay, so the sine of angle B, which is 52 degrees, to the length of side B, which is 4, will be the same ratio as the sine of angle A, and angle A is what's unknown, what I'm trying to find, is to side A, which is 3. So then I'm just going to solve this algebraically, and if I cross multiply, I get 3. Well, I'll go 4 times the sine of A first. Put that on the left. 4 times the sine of A is equal to 3 times the sine of 52 degrees. And dividing by 4 on both sides, I now have the sine of angle A is equal to 3 times the sine of 52 degrees divided by 4. And when I punch that into my calculator, I get that angle A, well, first of all, let's show it algebraically. I have to show angle A is equal to the inverse sine, because I know the ratio of the opposite over the hypotenuse, degrees over 4. So now when I plug that into my calculator and round to the nearest tenth of a degree, I get that angle A is 36 2/10 degrees. Okay, so again, when the angle is what's unknown, I have to use the inverse function to tell my calculator, look up the angle measure that has a sine, a ratio of opposite over hypotenuse in that ratio. So anyway, that was finding a missing angle. And then if I needed to find angle C, I would take 180 degrees minus the 52 minus the 36.2, and I could find angle C, which in this case would have to be an acute angle, an obtuse angle. Anyway, so let's go on to the second example. And this one we're going to just start with a word problem and have to draw the scenario. So we have a captain of a ship, and he sights a reef that's located so that the angle between the ship's course and the line of sight to the reef is 20 degrees. So he sails along his course another 8 kilometers, and then he looks again, and now he is at a 70-degree angle looking at the reef. So at this point, how far from the ship is the reef? So this is all about the drawing. So I'm just going to say this is the sort of the starting point, and let's just say that the reef is up here, and we'll put that at C, point C, and we'll make the starting point A, when he looks. And at the moment that he looks, his ship is on a course maybe this way, so this is a 20-degree angle. And his ship is going to go a certain distance, and after a certain distance, that angle, now looking back over to the reef, is going to be a 70-degree angle. So I'll call this point B when he looks again and marks the angle to the reef. So let's call this now, this is, side little b. I don't think that's involved in this problem. This is 8 right here. He sailed another 8 kilometers. That's right here. And we've accounted for the 20 degrees and the 70 degrees. And what we want to know is how far was the ship from the reef. So this is what we want to find, is this distance when he looks and there's a 70-degree angle. So this distance, I'm just going to call its opposite angle A. I'll call that side A. So what we're really trying to do in this is to find the length of side A. So when looking at this, I can use the sine of the 20-degree angle is to A as, and because this is the side I know 8, I really need to know what this angle is, angle C. So I can do that by knowing that this along this straight line is 180 degrees, and if this is 70, that this angle is 110. And then I know that the sum of the angles in the triangle has to be 180. So if I've got 110 plus 20, that's 130. So then this is the other 50 degrees. So now I can say sine of A is to A as sine of C, angle C is to side C. So is to A as the sine of C, angle C is to C. So the sine of the 20-degree angle is to A, which I'm trying to find, as the same ratio as the sine of angle C, the 50-degree angle, is to side C, which is 8. So cross multiplying here, I'll go A times the sine of 50 degrees is equal to 8 times the sine of 20 degrees, and then divide both sides by the sine of 50 degrees to isolate side A. So A is equal to 8 times the sine of 20 divided by the sine of 50 degrees. And when I punch that into my calculator and I round to the nearest tenth of a kilometer, I will get 3.6. So the distance A right here is 3.6 kilometers. And that's it. So this is all about a lot of practice with drawing diagrams, and it takes careful and close reading and maybe some trial and error. Good luck.